And I'll turn things over to group 462K, the Infinity Table team.
Sweet. So we are group 462K, and we're here to present our orbital shaker prototype, the Infinitable. My name is Alexander Davis, and I am a fifth-year mechanical engineering student at the University of Florida.
I am Colton Miller, and I'm a fifth-year mechanical and aerospace engineering student.
I'm Reagan Roberts. I'm a fifth-year mechanical engineering major.
I'm Chris Supik, and I'm also a fifth-year mechanical engineering major.
I'm Nina Sutcliffe, and I'm a fifth-year mechanical and aerospace engineering major.
I'm Georgia Williams, and I'm a fifth-year aerospace and mechanical engineering major.
Josh, you're muted.
And I'm Josh Watts, a fifth-year mechanical engineering student.
Sweet. So now we'll go over the agenda about what we're going to discuss today. First, we will discuss the customer's initial request. Then we'll get into the design subsystem breakdown. After that, we'll get into our product specifications. Furthermore, we'll talk about the evolution of our design throughout the semester. Then we'll give you a cost breakdown and then our path for future improvements of our design. The orbital shaker is to be created for integration into an existing microbioreactor design. Microbioreactors create an ideal environment for cells to proliferate. The existing microbioreactor comes equipped with a heated enclosure, a pipetting system, and an orbital shaker. Since the shaker table is integrated within an extreme environment, it was designed to be resistant to both heat and chemicals that it may encounter during experimentation. The orbital shaker also is required to fit within the existing enclosure without impeding any of the other subsystems. The table was required to mount both well plates and 15 and 50 milliliter tube racks. Most importantly, the table was required to enact 3 different shake patterns: orbital, which actuates cell cultures in a circular motion, linear, and double orbital, which actuates the cells in a figure 8. The speed, radii, and time that the system runs were required to be customizable with a maximum speed of 350 RPM and a maximum diameter of 25 millimeters. The graphic to the right shows the team logo for the Infinitable. The logo seeks to market the 3 shake patterns that the system can perform. Next, we'll look into the subsystem breakdown of the team's design. But first, we're going to get to the value proposition. The Infinitable provides value to the customer by allowing them to perform a multitude of experiments using one system. On the market, competitors do not come equipped with the customizable abilities our product has, such as shake pattern selection, radius selection, as well as the ability to interchange well plate and tube rack applications depending on desired experimentation. Our orbital shaker has an extremely user-friendly interface, removing hefty learning curves that come with operating some systems. Our product is also cost-effective when compared to on-the-market competitors, whose products offer much less adaptability comparatively. The first of the 4 subsystems is the well plate and tube rack subsystem. The system's main parts are the 2 plates that house the well plates and tube racks, the aluminum center block that threads the lead screws through, threaded inserts that match threads of the lead screws, and a spring-loaded ball bearing that relieves loading from being directly on the lead screws. The well plate is clamped directly on by the labeled top plate. The tube racks match the exact dimensional size of the bottom plate, allowing them to snap into place with extra security by 2 of the wing nuts in the middle holes. As lead screws are rotated, the center block can move linearly. With specific rotations of both the lead screws, orbital and double orbital motion is achieved. Among our initial design reviews, there was worry about the amount of weight being enacted directly onto the lead screws during experimentation. With this, we adapted the design to maintain a spring-loaded ball bearing threaded directly into the bottom of the block to relieve loading from causing any lead screw deflection. The next subsystem showcases the design's movement. Rails and carriages are used to allow system actuation. Some rails are fastened atop a spacer block constructed from aluminum. The spacer block provides a height change of the rail to match the heights of the lead screws shown on the center block. The bearings shown on 2 of the rail carriages also maintain spacers to keep the lead screws exactly parallel to the bottom base plate. 2 of the carriages maintain a dry running mounted sleeve bearing. The bearing sleeve mounts the other side of the lead screw, preventing them from being cantilevered. The NEMA 17s are mounted to a modified OTS part to match the holes on the rail carriages. When lead screws are actuated, both the motor and adjacent bearing carriage moves along the mounted rails.
The next subsystem is the structural base subsystem. This includes a 1/4-inch aluminum plate that is tapped and threaded, or has all the holes threaded to mount both the rails, the spacers, and the electronics housing. The electrical housing houses all the components such as the motor drivers and Arduinos to power the motors and control them. There are 4 rubber feet to secure the table to the shaker table to whatever surface it's working on, and these are threaded into extra long screws that go through the entire base plate. The limit switches are also mounted on extra long screws, so no additional fasteners were needed to attach the limit switches, and they were placed in a way that they still hit the outside carriages and could act as a hard stop just in case the system were to fail, and so the rails wouldn't leave so the carriages wouldn't leave the rails. And then here's our control box interface. So this uses potentiometers to control the shake pattern, speed, and time. The small buttons on the right are the system start stop and system on off buttons. And the large center button is the emergency start off. This cuts 12-volt power to the motors just in case anything were to happen. The whole system could be shut down and the motors will no longer have power to move. Lastly, there's the LCD screen, and this displays the information so that the user can see what pattern they're choosing, what speed, and the duration that they want. And here's the final CAD drawing of our the infinitive table shaker table.
Okay, now for a little bit about the product specifications of the infinite table that we are providing to the customer. In regard to the motion, speed, and orbit size of the table, our table is able to reach a maximum of 25 cycles a minute at a max diameter of 25 millimeters. It was able to execute linear, orbital, and double orbital patterns of motion. The user interface is composed of 3 buttons and 2 potentiometers. There's 2 smaller buttons, one to turn the system on and another to select the settings and start the program. There's another big push button to be used as an emergency stop should anything go wrong or the system needs to be stopped abruptly. The potentiometers allow the user to scroll within the settings to choose orbital patterns, speeds, and the runtime. There's 4 limit switches, one on either side of the rail that is used in calibration of the table. Should any of the limit switches be touched or actuated during the runtime, the table will recenter and continue its shake pattern. The top plate can incorporate well plates or tube racks depending on which of the supplied fastening devices is used. There's 2 NEMA 17s attached to 2 double-threaded lead screws, and that is the drive system of this table. The infant table is relatively compact with overall dimensions of 12 inches by 15 inches by 6 inches and is about 15 pounds. Lastly, the table is made mostly of aluminum or stainless steel parts, so we could adhere to the non-reactive and heat-resistant criteria. Here we have 3 GIFs showing the motion that we were able to achieve. On the left-hand side, you'll see the double orbital or the figure 8. In the center, you'll see the linear. And then on the far right, you'll see the orbital or the circular pattern.
Diving into some of the unique features in our specific shaker table. The first one, and probably the most unique aspect, is the use of lead screws for actuation. This allows us to adjust the radii of the patterns being set without physically manipulating the system. Another aspect is the inclusion of spring-loaded ball bearings on the bottom of the center block. This helps alleviate the loads from some of the lead screws and have a more clean actuation. Looking into operating the system itself, it's fairly simple. You can easily set each parameter using the control box, and it can quickly and efficiently stop and run the system at any point during operation. It's also fully customizable with being able to set each pattern or speed individually from each other. And we think we did a great job with the UI. We like how our control box came out, and we think it looks clean.
So there are 6 designs were chosen to be compared using the House of Quality. And the House of Quality weighed the 6 designs based on their adherence to the customer needs. One design was determined from the House of Quality study, and concept designs based on the winner were created focusing on adding features that the team believed improved the chosen system. And once concept designs were created for each of the subsystems, 4 trade studies were conducted by every group member and comparing each of the needs to one another. The rating percentage of each category was found based on everyone's results. The down selection matrices were created for each of the additional concept designs based on the original House of Quality winner. And the winning subsystem concept designs from the down selection matrices were chosen and combined to create a final system design that the team believed best met the needs of the customer. Since the start of this project, the design has evolved in a lot of ways. And this slide includes changes made to the structural base, the movement system, and the rails. And so originally, as you see in the top figure, we had selected a structural base that was made of 80/20, but then we later changed it to a 1/4 inch aluminum sheet. This is because it would not have been sturdy enough to hold all of the vibrations that would have taken place while the shaker table was in motion. And the change made in the movement system, it involved going from not having a ball bearing to having one. And this was decided to help with the load that was acting on both the center block and the lead screws. And then looking at the bottom figure, the original design had cantilever motors and rails. And because of the setup, as well as the load acting on it, additional rails were added to the opposite ends of each motor.
Further evolution came in the form of the top plate of our system. It was functionally changed to accommodate for tube racks. The plate is sized so that the tube rack can wrap around the sides of the plate. And originally, the friction from that was the main force securing the tube racks to the plate. However, with a full tube rack and at higher RPMs, we wanted to improve the security of the tube rack on the top plate. So we added threaded holes so that the wing nuts that we already were using could be used to thread through the tube racks and improve the overall security.
Sort of continuing on with that, there's a sort of visual representation of the tube racks clamping down onto that top plate with the 2 sort of wing screws going through the side holes that we made for them. The sort of function of that whole top plate, the idea was to have easy interchangeability with the well plates and tube racks, so they could just be very user-friendly and interchangeable. So along with that, the limit switch mounts were modified so that they could be more easily fit underneath the base plate. The old design wasn't quite long enough to have the limit switches interact with the blocks on the rails, so they would just kind of go over them and not engage. And it also made it more difficult to fasten them without having additional fasteners underneath the base plate. So when we were going through our initial designs and the initial testing, the rails we looked at were on McMaster Carr and had specified dimensions, specified sizings for like screws, positioning that you would use for the blocks or any mounts you would have for the blocks. And we found a order on Amazon that had a rail with similar dimensions and sort of distance specifications. But when it arrived, it turned out these dimensions were different, slightly different from what we anticipated. So with the NEMA 17 mounts and the bearing spacers that had to be attached to these rail blocks, the positions of all the screw holes had to be changed in order to allow for attachment to these blocks more easily. Continuing on with further evolutions in the design, the control box interface actually went through a few changes. So with the old design, actually didn't come up with a way initially to incorporate the big emergency stop button into the interface. And we figured also as well that we could space out the components a bit better and make it look a bit more clean for the final design. So as you can see visually there, the new interface does have that bigger hole in it in the bottom left where the emergency stop button would be placed. And you can also see that the position of the components was kind of changed around a bit to sort of have a better look and maybe easier interaction and easier interface. The lead screws also had to be modified. During initial testing, we would notice that the set screws that were in the couplers that would attach the lead screw to the NEMAs and make the whole drive system run, the set screws would either like vibrate and pop out, or the lead screws would sort of like not be fully attached by the set screws, and so maybe have a tiny bit of wobble to them. So the way to troubleshoot that for us was to grind one of the ends down a bit, as you see in the new photo there, that flat edge, so that there would be a flat surface for the set screws to fully attach to flush. That way the set screws wouldn't rattle around and vibrate as much as the system was operating, and the lead screws would have more attachment to the coupler. That way they may not rattle around or sort of slip out as much.
At the most basic level, our code relays information from the user to the motor drivers, which in turn runs the motors. This allows our system to run for the set runtime, pattern, orbit size, and speed as set by the user. Our code was constantly being updated as problems arose throughout the course, and the following are 3 of the most significant changes. Firstly, with the addition of functions. Taking the code from an initial development phase to a prototyping phase required these. In our initial tests, we wanted to get just the UI working as well as basic motor function. And once these tests succeeded, we added functions to clean up the code and to keep things such as the code to run the motors separate from the code to run the UI. Another addition was the time stop. This was a simple but necessary area we added. This was done to enable the customer need for a user set runtime. In testing, starting and stopping the motors was done through just the control switch initially. However, in the current iteration of the system will run cycles until the set time is reached. The final major change to the code relates to limit switches. Originally, our limit switches were designed to just stop the system if they were triggered. During testing, though, we found that our orbit was drifting to one side as the motors were running. To address this, we shifted the limit switch from being a fail-safe to a soft reset. So instead of stopping the system when triggered, the motors would recalibrate before continuing their current motor pattern.
This table shows the unit costs and the mass production costs for the different parts of the production. And so the OTS parts and the raw material costs, they were calculated by taking the sum of the prices of each part and the material used that was used to create the shaker table. And then the manufacturing costs were calculated by associating a cost per unit located on the device. The assembly costs were calculated using the Boothroyd and Dewhurst assembly time estimate sheet. And based on the sheet, the assembly time was estimated to take approximately 6 minutes and 30 seconds. But after we assembled it in the lab, it took about 15 minutes from start to finish. And this means that the assembly time cost would increase. The energy costs were calculated by finding the cost ratio of kilowatt hours and then calculating how much it would cost to run the device for an entire year continuously. And then the mass production costs column are 10% of the unit cost.
Due to time and resource constraints, there is much room for improvement left for our product. The first upgrade we'd like to make is to improve our movement and electrical systems so that our movement patterns can reach the desired output of 350 RPM. This would involve upgrading the motor drivers used in the electrical system to have a higher power output and replacing the motors so that higher RPMs can be reached. We would also like to improve the tolerances between the center block and lead screw interfaces, since the current tolerances are too large and can cause drifting in the system. One way to prevent this is optimizing the center block to take up less space and have less weight on the lead screws. After testing, we found that the current flex couplers in use allow too much uncontrolled movement, and we intend to use non-flex couplers to have more rigidity and precision in movement during testing. As mentioned, progress was limited by resources available. For the future, we would like to have a fully manufactured product to replace all the 3D printed parts. Due to a bottleneck in the manufacturing queue, our design enclosure was unable to be manufactured. The design we had for our enclosure was not optimal for 3D printing, so we decided as a team to leave out the enclosure from our final project. For the future, we would like to integrate this into our product. To continue to optimize weight distribution of our system, we are considering decreasing the size of our rails. It is also essential that we properly lubricate our rail system, and we plan to further research lubricants that are compatible with our system and project requirements. To optimize cable management, we would like to implement the use of wire tracks. This would make the assembly more user-friendly for the customers and protect the wires if chemicals splash out of the test tubes or well plates during movement. During testing, we found that the motor drivers generate a lot of heat. Though failure never occurred from this, even during endurance testing, as a preventative measure, we would like to integrate a CPU fan in the control box to keep the motor drivers and other electronic components cool. Thank you to all the sponsors, customers, friends, families, and mentors that joined us today for our presentation. Are there any questions?
All right. Excellent presentation. Thank you for sharing your design with us. Do we have any questions from our panelists? Dr. Banks, you're up.
Yeah, thank you. Really nice presentation. I am not intimately familiar with the customer requirements, but it seems like a key element of your product is the variety of different shaker paths that you can do, the figure eight, the linear, the circular, and it look like variations in between. Is that driven by customer needs? Is that just a cool thing that results from your architecture, or is it really responding to some performance benefit?
It was something that was required by the customer, and the customer needs to be able to achieve each of the 3 patterns.
Got it.
Okay. Sorry, I'm watching Dr. Banks flip. In order. Other questions? Alex, are you still with us?
Yes, absolutely.
Okay.
So if no one else is really gonna ask about the I'm not gonna really call it the elephant in the room, but you know, we've kind of already covered this throughout the semester, but I really just want to ask again, how did you end up deciding on lead screws, and how did that make it through the House of Quality, right? Is there, because with lead screws, right, of course, was there some or like a confusion in the customer need statement originally, that on the like 350 RPM that drove you to lead screws?
Yeah, as far as that, the confusion with the customer needs, initially, from what I remember, the only defined speed was with the orbital, and that one stated 350 RPM. And then the other ones didn't state a specific speed, but they were in cycles per minute. So I think the confusion was that the orbital it didn't really say cycles. So what we believe was that it wanted the motors to be 350 RPM. So it was just a little bit of confusion there. Yeah, I don't think we would have went with lead screws if that was the case, but.
Yeah, so that actually kind of leads into the next question that I had. And actually, Dr. Trauma's been asking this question for more of the other groups, but I'm going to steal it from him while I'm talking about the subject. This question that's kind of going around is not a trick question. It's a genuine question. Do you, after observing some of the other designs that the other groups have made and kind of doing the prototyping phase and actually seeing your design function in a real world setting, do you believe that this design is like generally the way to go and can be improved upon, or is there another completely different design that you think is more optimal for meeting all of the customer needs? And if there is one, do you have any idea of, if you were to do this project again, what you would switch to?
I think the biggest thing with our design was that you could change things like the radius and the different movements just through the user interface. And there's no mechanical changes that had to be done as with other designs. I certainly think other designs did things better, like getting better speeds than we did. But I also think we could get those speeds using nicer motors. But another cool thing I think with ours is that it can be programmed for theoretically any movement or any sort of pattern. And it's not really set with one or the other.
Yeah, in my opinion, there's just like every design sort of has its optimum things that make it better than other ones. And the main one for our design with the lead screws is, as Josh was saying, it can do any pattern, not just the 3 that were specified in the needs, but it could be programmed to do any one you would want. And there are ways still to improve it, to make it better than we already have it, to where it could get higher speeds. It could probably get better like resolution. It's just we weren't able to achieve that with what we did, but there are steps to where you could make it be one of the better ones.
And
Sure,
if we weren't to go into the improvement of this design, I think personally a lot of us were also at the beginning of the semester leaning towards one of the designs with the vertical NEMA motors and the kind of hub design, where the well plate was actually attached to those hubs, similar to the independent study that was shown to us at the beginning of the semester.
Sure, that's more or less what I was looking for. But to comment on what you were, I think what was being said earlier regarding being able to do any pattern, unfortunately, I don't think that's necessarily a feature that's inherent to your design because of the lead screws. I would argue that is more of specifically something that any design that operates with 2 axes, specifically in the XY plane, can accomplish. So for example, there were a numerous number of belt systems or the core XY systems that can also do that. Do you think that that might be the way you would move forward in a future design rendition of this project?
I think it's
Or
definitely
you-
something we could investigate. I remember another reason that we had leaned initially towards lead screws rather than belts was just a little bit of worry of the wear that would happen on belts. And we were trying to go towards something like lead screws where we thought maybe this is something that could prove to be viable for a much longer time than something made out of a rubber or a plastic material like a belt.
I mean, yeah, if I recall correctly, it needed to be able to run for 6 million cycles straight. And we just weren't confident that the belts would be able to do that over and over and over again without having to constantly be maintained.
And that sort of trails back to your earlier question about like down selection and things like that. That was something in the down selection process that sort of narrowed us towards lead screws rather than belts, was the worry of like tensioners and belt wear and factors like that.
Sure, I understand, and I completely understand your intention for trying to make this thing the most robust thing that exists out of all of the designs. But of course, it comes down to, I guess, what do you prioritize? Making this thing able to last however many additional years, opposed to a belt design, or something that can truly spin up to a 350 RPM without requiring the motors to spin at some ridiculous, maybe as a random number, 20,000 RPM or whatever, and experience some severe complications in direction reversals. It's possible that although your lead screws are very, very robust, when you actually spin your motors as fast as is required to hit the upper range of the customer needs, those direction changes at those speeds, maybe your motors actually become the thing that needs very consistent maintenance. So it's just things to think about, but I understand where your priorities are. And for where your priorities were, I think it was a very well-built design. So good job throughout the semester and facing those problems.
Awesome. Thank you,
Thank you.
Alex.
Thank you.
All right. Other questions from our panelists, and this can include the friends and family and supporters who are here in the audience as well. You guys are equal participants as panelists. Oh, okay. I think Dr. Banks has his hand raised again. Oh, you're muted.
You're muted.
Uh-oh. Dr. Banks, you're muted.
How's that?
Yay, there we go.
What about the cost of this as in terms of meeting the requirements, potential profitability, and how it benchmarks with other designs? It seems like a pretty robust system that might be a bit on the pricey side.
Yeah, so for the customer needs itself, there wasn't a set in stone price to manufacture this and get it built. It definitely is on the pricier side compared to what's currently listed on the market, but we believe that there's some value added in the fact that you're able to have so much customizability with what pattern you're doing, what speed you're running it at, and which radius. And rather than having to go out and maybe buy separate pieces of equipment that kind of experiment with cell cultures in different ways, the idea is that you would have a single unit that can kind of perform all that for you. I also believe that doing a little more research into our materials and our product choices, that we could probably drive down the unit cost to be less expensive than what was listed on the cost summary. But we just wanted to make sure that we put at least we wanted to overshoot, put more of a top line before we actually went in and got, more research onto how we could drive that down in the future.
Okay. So this is nominally sort of a high performance or a luxury brand of shaker table.
Yes, that's how like we would like to think of it for sure.
And I think there's also a lot of value in the like potential lifespan of it, and that there's not a lot of high wear parts on it, and the projected lifespan is pretty high or very high. And like I said, I think there's value in that as well.
Yeah. Rather than having to, you could have this thing for years and say, biology or like scientists in the bio area find that a different shaking pattern somehow like makes the cells grow more or something like that than the 3 ones that are more commonly used out there now. Instead of having to develop or like come up with another development, make a new table that can do this design that they come up with, you could just go into ours and reprogram it a little bit, and then it can execute that pattern for you without you even having to spend money on a new unit.
Awesome. Thank you.
So, so you guys are sort of in orbit around the question that I want to ask, which is, so you did the torture test, right? The life expectancy tests, and you guys passed that with flying colors. I have in my possession, because I am the as my wife says, the keeper, the hoarder of all kinds of weird things that are like, mechanical engineering things from the past. Some syringe pumps from like the 1960s that still run. And I got them on eBay, and they were incredibly inexpensive, which is why I have those instead of buying new ones. How does your design fail? Like once you run it for, however long it's going to run its entire operational lifetime, and then some, what's the weakest link that causes your system ultimately to break mechanically?
I do think it would probably have to go towards a motor failure, possibly a motor driver failure. We did notice when running the endurance tests that the motor drivers would heat up. It never caused any kind of glitch or failure in the system. So we would plan to implement, obviously, some kind of fan to cool it. But I think mechanically, maybe there could be some wear on the rails over time. But if they're kind of taken care of, well lubricated, I feel like the biggest failure points would be the motor or some aspect of the electronics.
I was going to say my guess would be the rails themselves, just because it's blocks on rails and kind of just relies on the ball bearings within the blocks and sort of the self lubrication that they have. And just like over time, eventually that might wear out and run out. And then at that point, it's metal grinding metal. And that probably can't go on for very long before failure. So it just ties back into researching ways to keep it lubricated.
And are you guys expecting the end users to do that? Like, is there an instruction manual like that comes with my garage door that says, oil this every 6 months or your garage door won't open?
I mean, it could definitely be included in some kind of maintenance along with the manual assembly plan, something like that.
Oh, okay. Oh, hang on. You just set off another trigger for me. So, assembly plan, does that mean that you're expecting your end user to assemble the parts? Like this thing comes as a kit that the user puts together? Or
So we plan to have it mostly put together, but I mean, if they were wanting to tweak around, if something ended up failing, I think it would be really smart to include some kind of manual assembly plan. It is kind of straightforward how everything attaches, however.
Okay, so so actually this is an interesting kind of line of discussion, because I've had the same chat with other student groups. So I'm, right when we jumped on, I was making the comment to Dr. Banks about all of a sudden feeling like I'm 45 years old, which that happens in a couple of days. So back in my day, right, back when we used to walk uphill in the snow both ways to school, it used to be that stuff was simple enough that you could fix it. I have, really fond memories of my dad had this really old radio that broke, the channel changer broke. And I, this is sort of how I discovered that I'm an engineer. I ripped the thing apart and realized that the thing that broke, quote unquote, was actually just a belt, and the belt wasn't broken. It just had come off of the cogs that it was on. And so I was able to just, put the belt back on the cogs and put the radio back together and hand this now working radio back to my dad. And it was like this, really cool moment of father-son pride that I, fixed his broken radio. But in 2022, 2023, I get applause from Dr. Banks. Planned obsolescence is like a thing, right? Like stuff is designed to break. It breaks on purpose. And the reason that designed obsolescence is a thing is because to keep your company in business, you have to keep selling widgets, right? Whatever those things are. The classic example is in the world of bowling alleys. There's a company that makes I think it's called Brunswick, that makes the pin setters in bowling alleys, and the company has gone out of business because they made such a good product that a bowling alley would buy the pin setter, and like 50 years later, the same pin setter would still be working. It just required, just very, very minimal maintenance. And so, thinking of this as a product for a potential, company, where is that boundary for you guys? Like you guys have basically designed like a tank, right? Like this thing is probably gonna at some point end up in my garage 20 years from now with my wife complaining, why don't I throw it away? So how do you stay in business as a company if you've designed something that's like so robust that nobody's ever going to need to buy another shaker table from you again?
I think that's a proud way to go out of business, is that you built like such a good product. And I guess this is obviously very theoretical, but I guess you just have to stay innovative and try new things and new products and ways to improve your old ones, give them a reason to want to upgrade. But at the end of the day, I think Brunswick should be proud that their product is so good that it never needs to be replaced. I don't like, as someone who likes to work on things myself, I don't like the idea of like planned failure. But I understand the business behind not doing that, but I get that our design was built by engineers and not by accountants. And so I guess that's why it's supposed to last forever.
Yeah, I was gonna say the engineer in me like kind of cringes at the concept of designing it for failure.
I
Yeah,
think
I
if
think-
anything, if we wanted to provide some kind of revenue behind it, we could definitely look into having some kind of maintenance troubleshooting team that maybe you could consult with for a price, something like that. But also I'm thinking there could be a lot of modularity and a lot of new pieces that maybe we could have to sell. There's a lot you could do with that top well plate tube rack system. We were also thinking at a time of including some kind of magnetic base where you can snap on different modules and pieces. So maybe we could even expand in that direction, having different things that you can mount to the top of it to perform your experiments.
I think also we went with a really kind of industrial design of our shaker table, and that might not be ideal for every customer. So I think we could also streamline our design to make it more like simple if you want to have it in like a classroom or like something like that. Also, we keep harping on the idea that like this table can be put in any pattern for its orbits. And I think we could also like market like upgrades or updates to our code so that they don't have to go in themselves, kind of like when you update your iPhone. Like, you make your iPhone, like, your phone's going to die eventually when there's a new update because like it starts working like crap because they don't have the updated code. I think we can do the same thing where our code isn't up to date. And we have to have them come in and get a new like Arduino or whatever.
Yeah, I mean, you could even use the code to unlock maybe new shake patterns that they're interested in. That could be something that they consult us for and that we could upload directly onto a device like that. But I think there's a few ways that we could try to make some more revenue stream out of something that's such a robust build.
Okay, so this is good. So I'm hearing like accessories, right? So it's that it's sort of the Snap-on model, right? So, or the Dremel model, right? Like you basically sell them the base unit, which never breaks, and then you add my another weird family. So my wife discovered that there's a Dremel attachment for woodworking. I've got a Dremel that I've had for years. And she just showed up one day with this Dremel woodworking attachment, and I'm like, that's awesome. Like, I love it. And now it's, of course, more stuff in my garage that she complains about. But so that's one possibility. But then this idea of like software on a shaker table, I think it's pretty interesting. Yeah, John's laughing. So pretty interesting, right? Like that's, I think, a novel idea where, you've got the orbital, the double orbital, and the linear shaker pattern, but it's sort of like an iPhone app, right? It's like, oh, different shaker patterns. You could do the smiley face shaker pattern, or the, expand the use of your shaker table into different realms of bioengineering and biotechnology using different possible patterns. You guys are the first group, I think, to, there are other groups that have sort of said, oh, you can customize the pattern, but I think you guys are the first ones to really articulate that that's its own separate like feature that you guys can add on to the capability after the customer's already bought the product, by giving them like new patterns, right? It's you get a what's the thing called? Is it Birchbox, where you get like a box in the mail that has like, different t-shirt or something every month? You guys could send them a different a different shaker pattern every month or something like that, right? I mean, I think that's very clever. That actually might be worth thinking about outside of the context of the capstone class.
It'd be even cooler if you could control all the functionality of it through some kind of Wi-Fi receiver on your phone. Maybe even have an app that kind of can market stuff that you can unlock directly from your phone that could maybe upload via Wi-Fi or Bluetooth onto the system itself. So definitely something to think about that could be very interesting to pursue in the future.
Yeah, the gamified shaker table.
Or you could have your app where you draw the pattern you want and the shaker table does it after you subscribe to subscription model.
After you subscribe, yeah.
Like, comment, subscribe.
Yeah.
Yeah, that'll be the premium version.
So for the for the benefit of the video, because the chat comments don't end up getting recorded, Dr. Banks says annual service / maintenance programs or lease versus buy sales model. If it is super robust and durable, your service cost should be small. Yeah, actually that's one that I encountered as well in my time in business. Leasing instead of selling, and then you get a continuous income stream. And then there's another comment from one of our gallery members. I would suggest a digital integrate. Oh, here we go. I would suggest a digital integration into healthcare software systems that capture information in real time to eliminate human error, as well as comparing analytics using AI engines. Yeah, that's pretty clever. So human error, right? Like, so for example, your our immediate customer is Professor Menezes, and up until this moment, we've imagined that a lab technician comes along and puts some cells in the microbioreactor and pushes a couple buttons and walks away. But what if the lab technician push the wrong buttons, right? And you're using the wrong shaker pattern. You need a shaker pattern that profuses nutrients into the cells, and what was accidentally selected is the one that breaks up biofilm, right? Like with this kind of software integration that you guys are talking about, the shaker table could actually detect those kinds of errors. And then also to this point, this is a good idea. If you are, so you guys weren't, well, this was sort of outside of the scope, but for next semester, we're going to add ODFI, so optical density and fluorescent intensity, which measures the health of the cells in the well plates that are being shaken by the shaker table. You could actually have like an onboard computer take those measurements and adjust the pattern right, in response to whether there's a biofilm that's forming or whether there's a low nutrient level or you know, if the ODFI is not doing what it's supposed to, you could change the shaker pattern on the fly to improve the health and viability of the cells. That's I think something that, and I'm, you know, I haven't dug around in great detail in the world of shaker tables. I sort of know what, you know, their cost points are and stuff, but I don't think that feature is available on any commercial shaker table that I'm aware of. It's sort of an active feedback shaker selection capability to keep your cells happier than they would be if you just sort of set it and forgot it. So
Yeah, you could implement it in the same way as like our calibration does, where it does like a soft reset, where like it stops whatever pattern it's doing whenever it notices that it is off and kind of just resets the center, and then does the pattern that the AI would deem is the right one to fix those measurements.
Yeah.
Something along those lines.
yeah, that's cool. All right. Well, so we've we've drifted a little bit away from the actual design, but this is why we do capstone and why we've got you know, these interactions, so that we can kind of talk through these ideas. And you know, some of this stuff that we talk about in these presentations and interactions ends up becoming a customer need in a following semester. So that's, I actually like that idea enough that I'm going to talk with Dr. Prasad and see if maybe we can implement that, because what I've been struggling with is, you know, okay, yay, ODFI, right? You take the measurements, but then what do you do with it? And the idea of taking that measurement and using it to like actively update the shaker pattern would be a very interesting capstone project, which would very clearly differentiate this shaker table as a product from other stuff that's on the market. So okay, yeah, I was excited already, but now I'm like super excited, because this adds a whole new dimension to what we might be doing next semester. So and I am looking at the time, and as you guys know, you've known me for probably a year now, those of you that also survived MEC 2. I have a okay, hang on, there's another thing in chat that says Little Bird told me that this is a real world customer ask, and reasonably speaking could be distributed to the market. Okay, so there's a hint that this might actually be something worth pursuing as a commercial product, and we're getting a little bit of feedback from it looks like an insider out in that market that this might be valuable. So cool. Anyway, okay. So what I was trying to do was wrap things up, because we were supposed to stop at 6, and I appreciate you guys sticking around with me for an extra 10 minutes so that we could talk through all these ideas. That my kind of final thing that I want to say is, you know, just to recognize that you guys are done. You survived. If you took MEC 2 and MEC 3, what a lot of my faculty colleagues describe as the final boss in the mechanical engineering curriculum. And you guys came through with success and flying colors and a really good design and some sort of interesting thought experiments for what we might do moving forward. Next semester, we're just, as I said, going to continue working on shaker tables, integrating ODFI, and including basically survivability testing in extreme temperatures. So we're going to put them in an oven and bake them and see how they do, and then put them in a freezer and freeze them and see how they do. And do all the endurance and torture testing in those extreme environments, and add the ODFI capability to measure what's going on with the cells on the well plates. So your design should be very competitive in that process, but we're going to do the exact same thing. We're going to basically, that we did this semester, take all of the designs, give them to next semester students, and let them do house of quality to select which ones they want to pursue for prototyping. So as you're sort of, you know, wrapping things up and putting pieces in place as you're graduating, just remember, the more information that you can sort of leave to convey to the next group, the greater the chances are that this idea of your design will continue into the next semester. But I think this is a very good design. Like I said, it's built like a tank. So anybody that's pursuing the, I want the shaker table to last forever, kind of hedgehog concept, I think should look very seriously at your design. So anyway, I want to thank you guys again for sharing your design with us and sticking around a couple extra minutes to talk through these things. Congratulations on finishing the capstone sequence. And I think I'm good. So we'll leave you guys the room if you want to debrief.
Awesome. Thank you so
you.
much.
Thank
Thank
you.
you.
Yeah.
Thank you, everyone who joined too.
Yeah, good
Thanks.
job, guys.
Thanks for the invite. See you guys.
Have a good
Congratulations.
one.
Yeah.
Thank you.
All right. Take care. I am out of here.
All right. Thank you.
Yeah.
Have a good one.
Thank you.